All right. Hi, everyone. Welcome to the keynote lecture. So we have David Beckay, who's, can you hear me?
Yes, I can hear you.
Yes.
Okay, great. So David, you can put your slides and yeah, I'm gonna do like a very brief introduction and yeah, so we're gonna put everyone as a panelist so you can ask questions. Great. So yeah, so thank you for coming. Thank you for joining the VMACS Virtual Junior Macro Conference. Today, for our last session of the day, we have David Beckay, who's going to present the keynote lecture in honor of Emmanuel Fari. We are very sad to have lost Emmanuel recently. Emmanuel, as we know, have recently started a new agenda on the foundations of aggregate production with David, his former student, David Beckay, and we are really excited to have David present to us in the honor and the memory of Emmanuel macro as explicitly aggregated micro for an hour. Go ahead, David.
Great. Well, thanks very much. I seem to be having some issues with my video. It says the host has stopped it. I'm not sure if there's something I can do about that or not. But you don't need to see my face. I guess it's fine.
Yes, sorry, that was me. That was something that got reset on the settings. It should be fine now.
Oh, excellent. Okay, thank you very much.
Sorry about that.
Thanks a lot, Abdu, for the introduction. Thanks to everybody for coming today, and to the organizers for giving me the opportunity to give this talk, which is in memory of Emmanuel. Emmanuel was a beloved colleague, mentor, and friend to many of us in economics. And before I start, I just want to say a few words in his memory. As we all know, Emmanuel was an exceptionally gifted economist. His publication record, the quality of his papers, they really speak for themselves. And I don't need to say anything about that. He was somebody who really deeply cared about ideas. But as his friend, I also knew that he cared deeply about people. He was an incredibly generous and gentle soul. There were many of us, senior and junior, who relied on him for his support, for his encouragement, and for his advice. And he really was a role model for many people, I think, not just as a scholar, but also as a human being. Unfortunately, there's really nothing I can say today that is going to do his memory justice. I still can't believe that he's gone. It feels like a dream still. And I also, looking back, find it hard to believe that someone like him could have ever been with us at all. Working with him very intensely on this research agenda for the last few years was better than winning the lottery for me. It really is a period of my life that I'm going to cherish forever. So during the last few years, Emmanuel and I had been studying and contributing to the literature on the so-called aggregation problem. This is one of the oldest problems in economics. Arguably, it is the oldest problem because the first piece of technical economics, Francois Quenet's Tableau économique, that was written before The Wealth of Nations, was trying to deal with the question of how to go from micro behavior to reasoning about aggregate objects. Now, this is a very old problem, and Francois Quenet's Tableau économique gave rise to general equilibrium theory, and general equilibrium theory led to the welfare theorems and the Walrasian project to construct macro from the grounds up. Now, this grand vision was derailed a little bit in the 70s because there were a series of negative theoretical results that basically showed you that pure reason is not going to work in thinking about these questions. Basically, theoretical results showed that restrictions that you place on micro behavior, like the idea that demand curves are downward sloping, that preferences are transitive, that you have diminishing returns to scale at the micro level, they don't actually imply that any of those properties have to hold at the aggregate level. And so without more structure or without more discipline on the theory, there's really not much you can say in general. Now, of course, in recent times, there's been a huge explosion of work on heterogeneity, both on the household side and on the firm side, building on the pioneering work that was done in the 1980s and 1990s. But what's different today relative to what people were doing in the 70s is that now we have access to much more micro level data than people did in the 70s. And the scope and scale and availability of this data is increasing day by day. So for example, there's a bunch of countries now that are making available to researchers their firm level VAT transactions data so that you can see the universe of firm-to-firm transactions at annual or even sometimes higher frequencies. So the idea here was we really wanted to contribute to the project to build flexible theories of aggregation that allowed us to really take advantage of all of this data and to try to make sense of it, because otherwise it's overwhelming. So we wanted to have theories that are flexible enough that they can consume as much micro data as the researcher basically has to supply. So broadly speaking, this means that you have to confront two different kinds of heterogeneity when you want to think about these questions. Heterogeneity on the household side and heterogeneity on the firm side. So on the firm side, you have different households that are consuming different goods and supplying different factors of production. On the firm side, you have an input-output network of heterogeneous producers that are consuming and supplying resources to one another. And the objective is to try to develop a general approach to the theory and measurement of propagation and aggregation with both kinds of heterogeneity. Now, of course, this idea is very, very big, and there's been very, very many people who have worked on it in the past and who are working on it in present. And I'm really not going to try to give you at all a sense of the literature as a whole. Instead, today, what I'm going to try to do is just give you a flavor for the approach that Emmanuel and I had for thinking about these kinds of questions. Over the last few years, we wrote a series of papers that studied these questions, always using more or less the same methodology. So the techniques that we developed, it turned out, were amenable to generalization and extension. And so I'm going to try to give you a flavor for what that was about in today's talk. So the talk is going to sort of sample from a bunch of different papers that we wrote. We wrote papers about aggregation in inefficient economies, aggregation in non-linear economies, economies that have heterogeneous agents, intermediate level aggregation. So if you want to think about aggregating at the level of, let's say, an industry rather than the whole economy, open economies that are engaged in international trade, the micro foundations of aggregate production functions, and even things like non-neoclassical economies that have things like entry and exit and increasing returns to scale and nominal rigidities. This was and there were, as you might imagine, there was lots of ongoing things that we were planning to do and things that I hope to be able to continue in Emmanuel's absence, as hard as it will be to do. So to give you a flavor for what we were doing, I think it's helpful to start by setting the scene and talking about some of the sort of classical aggregation formulas that were out there already. So the most famous one is the one due to Bob Solow that I'm sure everyone's familiar with. Bob Solow in the 50s, what he showed was if you have an economy that has an aggregate production function, so you just postulate a structural relationship that gives you aggregate output, then the total derivative of aggregate output can be written, of course, in terms of the contributions of the different inputs into your aggregate production function. Here I'm denoting that by capital L. This could be, these are the factors of production, so like labor and capital are the standard ones. And then contributions that come from whatever parameters index the production technology itself. That's what we think of as aggregate productivity. And what Bob Solow showed was that if your economy is competitive, then the elasticity of output with respect to these inputs, the factors of production, is just given by the sales of these factors as a share of GDP, which I'm denoting here by capital lambda. So this allows you to do very simple counterfactuals without knowing anything, really much information about the economy at all. So if you were to ask, of course, what would happen if we increased the supply of labor or the quantity of capital in the economy, how much would real GDP increase? Well, this result tells you that the answer is just sales of that factor, the factor income share, multiplied by the change in the quantity. Now, more prominently, this formula is used to measure movements in the economy's production possibility frontier. So if you subtract out output growth from input growth, then this allows you to recover changes in aggregate productivity. Now, in the 70s, Chuck Halton greatly generalized this result. He basically showed that this same equation continues to hold even in basically any Arrow-Debreu economy you write down. So even when you have heterogeneous agents and input-output linkages and they're as complex as you like, you can still write this equation down and it's correct. And furthermore, this object that we used to call aggregate productivity is now itself consists of a weighted sum of microeconomic changes in productivities at the micro level. So here, AK is a Higgs neutral shifter changing productivity for some producer K. And lambda K is the elasticity of aggregate TFP with respect to micro TFP. And what Chuck Halton showed is that lambda K, this elasticity, is just the sales share of this producer. So these lambda Ks, they're oftentimes called Domar weights. And these two equations collectively give you a foundation for Domar aggregation, which basically allows you to break up changes in real GDP into the underlying microeconomic sources, technological sources. Now, importantly, this is not a definition. This is a theorem, and it's going to fail in certain circumstances. And so that's precisely where my research agenda with Emmanuel was going. Now, these formulas, they're very useful for doing measurement. So for example, measuring aggregate productivity, but they're also useful for doing simple counterfactuals. So for example, if I said, what would happen to aggregate TFP in general equilibrium if Walmart became a little bit more productive? This formula tells you that the answer is just given by the sales share of Walmart. And you really don't need to know anything else. So these are incredibly powerful irrelevance results. What they're telling you is that the disaggregated details, like the input-output network, the way the factor markets look, the returns to scale at the micro level, the elasticities of substitution, the distribution of wealth and the marginal propensities to consume, the degree of openness to international trade, the initial level of aggregation you start out with. None of these things really matter for being able to answer these kinds of aggregate questions. You can abstract away from all of this detail. Now, given this generality, if you put Halton's theorem and Solow's result together, you get a first order approximation of how real GDP in your economy is going to change. Given this approximation, it's very tempting to jump from this equation to a global nonlinear version of the equation, which is to say that output is given as a Cobb-Douglas aggregate of labor and capital, let's say. And this jump is very perilous. And it's precisely in this step that basically the rest of the talk is going to be spent. So the reason the jump is perilous is because of the limits to Halton's theorem. So basically, Halton's theorem is going to fail if you have inefficiencies in your economy, which we might think are very important and are worth studying. But Halton's theorem is also going to fail at higher orders of approximation that are relevant for understanding nonlinearities and for understanding big shocks. Furthermore, Halton's theorem cannot be used to answer questions about co-movement of variables. So for example, although at the aggregate level, you could write this first order approximation, you cannot use it to understand, for example, the elasticity of substitution between labor and capital at the aggregate level. If you were to use a Cobb-Douglas formula, you would of course get the wrong answer, even to a first order. So for these kinds of questions where you have inefficiencies, non-linearities, or questions of co-movement of variables, or questions that are less aggregate than just real GDP, these disaggregated details are going to start to matter. But they're going to matter in ways that we can wrap our head around. And so the idea is to try to build new theories of aggregation for inefficient and nonlinear economies. So in our work, we found it very useful when we were thinking about these kinds of problems to break up the determination of output into two components. Basically, you can think of the amount of output that the economy produces as depending on some parameters that index the technology of the economy itself. So here, for example, I'm going to represent that using a bunch of scalars, AIs, that basically give you TFP shifters at the level of individual producers. But also the amount of output you produce is going to depend on an endogenous object, which is the allocation matrix of your economy, which I'm going to denote by script X. And intuitively, what the allocation matrix is doing is it's giving you the distribution of resources across competing uses in the economy. So for example, what fraction of steel produced in the US gets sent to General Motors? That would be something in the allocation matrix. And together, the allocation matrix and the productivity, the technology of your economy will pin down the amount of output that you're capable of producing. Well, therefore, we can say that any change in aggregate output in response to disturbances have to either come from changes in technology for a given allocation matrix or changes in the allocation matrix for a given level of technology, at least to a first order. Now, viewed like this, you can think of Halton's theorem really as an envelope theorem. So what Halton's theorem says is that because of the first welfare theorem, real GDP is going to be maximized in equilibrium. And that means that we really don't have to worry about this reallocation term. The reallocation effect in a competitive economy has to equal 0 and can be ignored. Furthermore, again, because of envelope conditions, it turns out that the elasticity of output with respect to technology is given by the sales shares of the individual producers that are being subjected to technological change. And so putting these two pieces together gives us Halton's theorem. But of course, as you might be able to anticipate, if you have an inefficient economy, then both of these statements are going to be false. So what we're going to do is we're going to try to capture arbitrary distortions in the economy using wedges that basically act like implicit or explicit taxes. And these wedges are going to distort the allocation of resources in whatever way you like. And of course, once we introduce these wedges, then equilibrium output is going to be a function of productivity and the wedges that you have that are distorting the allocation. This is because in the Walrasian setup, the allocation matrix of the economy depends on productivity and the distorting wedges itself. So now to think about a distorted economy, one with inefficiencies, we're going to have to introduce a little bit of notation, unfortunately. So you might already be familiar with the input-output network of an economy, which I'm going to denote omega. Omega basically tells you how much, if you view the economy as a giant matrix, how much does agent I or firm I spend on good J as a share of I's revenues. And so this matrix omega is keeping track of all these expenditure shares. But because there are wedges, there's also going to be a different notion of an input-output matrix, which is a cost-based input-output matrix. So the cost-based input-output matrix tells you how much I spends on J as a share of I's costs rather than as a share of I's revenues. And remember that the wedges are driving a wedge between the price and the marginal cost. And that's what gives rise to a difference between the cost-based and the revenue-based input-output matrix. So omega tilde here is the cost-based and omega is the revenue-based. Given these input-output matrices, we can construct Leontief inverses. So we have a revenue-based and cost-based Leontief inverse, and these capture the exposure of agent I to a product J, taking into account both direct linkages and indirect linkages in revenues and in costs. And finally, we're going to have to keep track of final demand in this economy. How much is the household spending on the different goods and services that the economy is capable of producing, which we're going to capture with some vector B you can think of as the budget shares of the final consumers. Now, as a principle of accounting, it's the case that if you multiply final demand by the Leontief inverse, the revenue-based Leontief inverse, you will recover the Dolmar weights. Remember, these are the sales shares. And these are the objects that were so key according to Halton's theorem. But by analogy, we can define cost-based Dolmar weights, which just use the cost-based Leontief inverse rather than the revenue-based one. Remember that if there are no wedges, these two things would be the same. But in general, they won't be. So intuitively, the cost-based notions are capturing exposure in costs. So if you think of omega tilde here, it's capturing how I is connected to J directly. So I is buying something from J. Psi ij, which is the Leontief inverse element, is giving you the direct and indirect exposures of I to J. And finally, lambda tilde k, which is the cost-based Dolmar weight, is giving you direct and indirect exposure of the household to K. So now we're in a position to state a generalization of Halton's theorem with distortions. So as I mentioned before, changes in real GDP are either due to changes in pure technology or changes in the allocation matrix. And with inefficiencies, we can expect that both of these legs of Halton's theorem are going to break. So here's what to replace them with. So in a distorted economy, we can say that the change in real GDP in response to a productivity shock is given by a pure technology effect, which is equal to the cost-based Dolmar weight of producer K, and a reallocation effect, which has to do with the cost-weighted sum of changes in factor income shares in the economy. So lambda L here, remember, is the factor income share of factor F, and lambda tilde F is the cost-based factor income share of factor F. So by looking at this equation, you can immediately see how this is going to give you Halton's theorem when the economy is efficient. Because in that case, lambda tilde is equal to lambda, and the weighted sum of factor income share changes has to equal 0, because in a competitive economy, the factors are gonna earn 100% of the income. So the sum of the factor shares has to equal 1. So I'm going to show you by using 2 examples exactly how each leg of Halton's theorem is going to break. The first example is going to show you why we need the cost-based Dolmar weight instead of the revenue-based Dolmar weight. Consider a simple economy that's just a vertical chain. So labor enters at the end of the chain and is passed by each producer downstream to the next producer. So producer K is transforming linearly inputs from K-1 and giving them to K+1. And at every step, there's a productivity shock AK and potentially a markup or a wedge mu K. And now we want to think about what happens if there's a productivity shock to producer K. Well, if you recall that the formula that I showed you said there is going to be a pure technology effect and potentially a reallocation effect. Pure technology effects in this economy are very simple. The cost-based Dolmar weight of every single producer is just given by 1. Why is that? Well, every producer in this economy is 100% the costs of its downstream suppliers. So every producer's cost-based DOMAR weight is just 1, because it's 1 times 1 times 1. The sales share of these producers, of course, is not always going to be equal to 1. That's because the sales share of producer K is going to be reduced by the amount of wedges that are downstream from K. And so if everybody leading up to K has lots of high wedges placed on their output, then the sales share of producer K is going to be artificially lowered. And so, of course, in this economy, you should expect the pure technology effect to be equal to 1. The elasticity of output with respect to a TFP shock is, of course, 1, because it linearly gives you more output, 1 for 1. But the sales share is not reflecting that fact. Now, in this economy, there's only one factor of production, which is labor at the end of the chain. And the labor share is not going to change if I change productivity of one of these producers, if the wedges are being held constant. And so therefore, in this economy, the change in the labor share is 0, and therefore the reallocation effects are 0. This is intuitive because in this economy, there's no scope for reallocation of resources. There's only one feasible allocation of resources where labor enters and go all the way down to the household. And so understandably, there's not going to be reallocation effects. Nevertheless, you cannot use Halton's theorem for this economy. Now let's consider a slightly different economy where there can be reallocations of resources. So this is the simplest economy you could have, where a household is purchasing from n different producers, and every producer is linearly transforming labor and competing for the other producers for the joint labor market. And then they sell their goods to the household. Now, every producer K in this economy also could have a productivity shock, and every producer in the economy is going to have a markup or a wedge. And then the consumer at the end is combining consumption goods with some elasticity set as 0. The allocation matrix in this economy is just a simple vector that tells you what's the share of labor going to each of these producers. Now let's think about a productivity shock to K. Applying the formula again, we should expect there to be a pure technology effect and a reallocation effect. The pure technology effect in this economy is very simple. It's just the sales share, like it was in an efficient economy. So the first leg of Halton's theorem in this example happens to hold because there's no intermediate inputs. There's nobody downstream from 1 who is double marginalizing 1 by putting wedges on their output. Therefore, the sales share is a correct estimate of the elasticity of output with respect to the productivity shock, holding fixed the allocation matrix. But of course, in this economy, there are going to be reallocation effects. When K becomes more productive, resources are going to flow away or towards K, depending on the elasticity of substitution. And that's going to have an effect on output to a first order. Because there's only one factor of production here, the reallocation effect is just given by the change in the labor share of income. In particular, if the labor share of income declines in response to the shock, then reallocation boosts output. The reason is if the allocation, the labor share declines, that implies that resources are being directed to producers with higher wedges, because these wedges, of course, are earning revenues. They act like taxes or markups. And so if the labor share declines, that means that you're sending resources to parts of the economy that are more heavily marked up. But the inefficiency of a markup is that it makes some producers produce too little. So if this shock is redirecting resources towards parts of the economy that are heavily marked up, this reallocation is going to boost output because it's sending resources to parts of the economy where the marginal product is higher. But the key observation is that all of this information is picked up by the change in the labor share. You don't actually need to know what the wedges are or what the elasticity of substitution is. All you need to be able to track is payments to labor. Now, of course, this is an endogenous object. And so you can solve for it and see that it does, as you might expect, depend on the elasticity of substitution and the pattern of wedges in this simple example. So these results can be extended also to environments where the wedges themselves are changing, which is very important because we don't think that these wedges are necessarily primitives. They're going to be things that evolve themselves in response to shocks. And this gives us a complete characterization of pure technology effects and reallocation effects in arbitrary economies, basically. And here we can see that the details are going to matter. Why are the details going to matter to a first order? Well, first of all, these cost-based objects depend on cost-based input-output networks. They're not something that you could just pick up from accounting data by looking at sales shares. Furthermore, these formulas depend on changes in factor income shares. These are these endogenous objects that are going to depend on things like the elasticity of substitution, the returns to scale, what the factor market looks like. And these things are going to capture how these forces are going to shape reallocation when you think about aggregate output. Now, the other thing that we do is, of course, these changes in factor shares is an endogenous object. But what you can show is that these changes in factor shares themselves can be solved for in general and written in terms of the primitives at the micro level. So this equation here, which I don't have time to explain the intuition of, basically tells you how factor shares are going to change in equilibrium as a function of elasticities of substitution and parameters that are shaped by the input-output network at the initial point that you take the derivative. And so these are going to combine together to give you in equilibrium how factor shares change. And then given the change in the factor shares, then you know how output is going to change. And this is where the micro information is going to creep into these aggregate questions. So using this formula, we can now do growth accounting with distortions. So you can think of defining aggregate TFP now, just as Solo did, by looking at changes in real output net of changes in inputs, which are the primary factors of production. And of course, this change in aggregate productivity now consists of two components: pure technology effects that are driven by the technology shocks directly for given allocation matrix, and changes in the allocation matrix itself that are going to give you TFP effects now. And this allows you to do these decompositions of the sources of aggregate TFP growth without imposing any parametric assumptions on the production functions of the economy. You want to contrast these kinds of estimates, these kinds of formulas, to decompositions that are out there in the literature that are a bit more statistical. They're not derived from general equilibrium models. The most famous ones of these are Bailey, Halton, or Oli-Pekis. And usually what these do is they write an aggregate TFP index. So for example, sales weighted sum of TFP shifters. And then they decompose this into a within and an across effect. And then the interpretation that's often given to these decompositions is this one is the technology or the pure within firm effect. And this one is the reallocation effects that come from shifting resources across firms. And what I want to say is that these interpretations are actually invalid. And these formulas, if you're interested in answering these questions, you shouldn't really be using these formulas. You want to use the formulas that came out of the theory. The reason is because these formulas detect reallocation effects in cases where they unambiguously shouldn't. So for example, in efficient economies, if you compute an object like this, you're going to get reallocation effects. Not to mention that in efficient economies, this actually is not a definition of aggregate TFP. This is just some ad hoc object. It's not output growth net of input growth, which is the object we're interested in decomposing in the first place. Furthermore, these decompositions also pick up reallocation effects, even in economies where there's no reallocations happening. I don't have time to go through the details of this, but basically you can imagine even in economies where the allocation of resources stays constant, the sales shares can change. But that doesn't tell you that resources have been reallocated. And so we think this represents a real advance relative to sort of the older statistical based decompositions that people were doing. So to give you an example of how you could use this, we took this decomposition and we applied it to the US to try to decompose the sources of aggregate productivity growth in the US. For our application, we used firm level estimates of markups as the wedges in the economy. So you can estimate firm level markups using different approaches, and we tried different ways. So you can use user cost of capital calculations to try to figure out pure profits, and from that you can deduce markups. You can use production function estimation approaches where you recover markups as the gap between output elasticities and expenditure shares. And you can also do more naive things where you just look at accounting profits, you take out depreciation, and you try to use that as a measure of pure profits and get markups that way. But given that you can estimate these measures of firm level markups, what you can then do is you can combine these firm level estimates with input output information to compute changes in aggregate productivity and the sources of aggregate productivity for the US. So here's what we found when we used this formula. The blue line here is changes in aggregate productivity, output net of input growth in the US. And what you can see is from 1997 to 2014, it grew by roughly 16 log points. The other two lines are decomposing the effect into changes that are due to pure technology shocks and changes that are due to reallocation of resources in the economy. And what you can see, the red line, which is the one that measures reallocation effects, is very large and is responsible for explaining half of the trend. Now here we're using the user cost markups. You get similar numbers if you use other estimates of the markups. And what this points to is that these reallocation effects are very powerful. And they're explaining roughly half of TFP growth in the US over the sample period. Now, when we first saw this, we were very surprised. We didn't understand where it was coming from because the markup data that we were feeding into the formulas, if anything, they told us these markups are going up. And so maybe you're expecting the US economy to becoming less and less competitive, and this should result in lower and lower productivity growth. But if anything, we're seeing the opposite in this picture. Now, thinking about the formula a little bit actually makes it clear exactly what's going on. And it actually led us to discover this fact in the data that we were not aware of, which was that the growth in markups in the US on average has primarily been driven by composition effects rather than within firm effects. So here, the blue line is showing you the average markup for the US economy, the aggregate markup over time, using the user cost approach. And you can see that it's been growing modestly over time. And then you can break up this growth just statistically into a within and between effect. And what you can see is that the pattern in the trend is primarily being driven by between effects. What this is saying is the reason that markups in the US have been growing is not because every firm has been putting up its markup. It's because the high markup firms have been getting larger over time. Now think about reallocation effects. If the firms with higher markups are expanding over time, then this means that firms that were inefficiently too small are now using more resources than they were before. And this, of course, is going to boost productivity relative to the previous situation. And so this explains why the reallocation effects, because they're driven by these composition effects, are actually boosting aggregate productivity over the sample. Now, to highlight the importance of having access to firm level disaggregated data, you can repeat this exact same exercise, but instead of using firm level markups, you can use industry level markups instead. And here's the breakdown you get. You can see that aggregate productivity is still growing by something like 16%, but now the breakdown between reallocation and pure technology effects is very different. When you use industry level data, not only do you get the magnitude of the reallocation effects wrong, you also get their direction wrong. Intuitively, what's going on is that the reallocations are happening within industries across firms. And so once you aggregate to the level of the industry, then you don't see it anymore. And so therefore it disappears. And you get very similar numbers if you use other kinds of markups. And this illustrates really the importance of having disaggregated data and taking disaggregation seriously when you have inefficiencies in your economy. Now, this is not the only kind of question that you can answer using these methods. These are all questions about measurement and decomposing the data. But you can also ask counterfactual questions. What would happen if something were to change in an inefficient economy? Now, a very popular question that people oftentimes want to ask is, given that our economy is distorted, what would happen to aggregate productivity if we remove these distortions? So for example, what are the welfare losses or what are the productivity losses from markups in the US? You can use the allocation matrix to think about this question as well. If you think about starting at an efficient point and perturbing the allocation matrix towards an inefficient allocation, which is what the markups are going to do, then you can think of the second order change in output with respect to the allocation matrix as measuring exactly to the second order the losses from these markups in your economy or from any other kind of distortions in your economy. Now, what's interesting is that you can show that this formula, which looks kind of abstract and difficult to look at, is actually also equal to a much more familiar formula, which is to say that the losses from inefficiencies in the economy to a second order can be written as changes in the wedges in the economy times changes in the quantities of the objects that have the distortions placed on them times a half weighted by the Domar weights. Now, this might be familiar to you because this is base times height times a half. So these are triangles. And what this is saying is that the loss function in general equilibrium is really just a Domar weighted sum of deadweight loss triangles, a la Harburger. And what's nice about this is that this is a formula that's predictive rather than prescriptive. So it applies in environments in general when you want to study the effects on aggregate TFP, independent of what motivations you have about welfare. You don't need compensating transfers to neutralize welfare effects, which is something that the previous literature emphasized. Now, stated like this formula is useful because it tells you, again, how the micro details are going to matter. Because obviously, you need to know where the wedges are, and you need to know how the quantity of every object that you have a wedge on is going to change in response to the presence of a wedge. You can also see how input-output linkages are going to boost the welfare costs or the productivity costs of these distortions. Remember that if you have intermediate inputs, that's going to boost sales over GDP. And these numbers are just sales over GDP. So the more intermediate inputs you have, the bigger are the losses that are associated with the presence of these Harburger triangles. Now, using this formula that I showed you earlier, the one that we saw here, these propagation equations, we can solve out also for what the distance to the frontier is in terms of the microeconomic primitives. So again, you can very simply write the loss function of the economy in terms of the elasticities of substitution inside the production network at different nodes, and some statistics that are related to the initial input-output matrix at the initial point. And this highlights the role that elasticities of substitution play and the input-output network plays and the wedges play in determining the losses from distortions. Now, given these formulas, we can, of course, put some numbers to these to see how important these forces are going to be. So you can try to calibrate a model using the best available data. You can use input-output tables from the DEA, and then you can take estimates from the literature about elasticities of substitution to populate this formula. So for example, there's going to be elasticities of substitution for households across different consumption goods. for firms between value added and intermediate inputs, across intermediate goods in production, between labor and capital, within firms and industries. Basically, you can have arbitrary patterns of elasticities of substitution. And as much information as you have, you can use these formulas to try to populate. So here's what you find about the distance to the frontier in the US over time using this information. So we compute the distance to the frontier in 1997 and in 2015 using the firm level markups data, using the 3 different approaches to estimating markups. And what you can see is that across the board, the distance to the frontier has gotten larger over time. Now, at first, this might be surprising because I told you that reallocation has improved aggregate productivity. But what this is telling you is that although reallocation has improved aggregate productivity, the frontier has moved even more quickly. And therefore, the gap between the allocation we have and the optimal allocation has expanded over time. And this is because the dispersion in the wedges, which you can see here, has gotten larger. And it's causing greater and greater losses. Furthermore, these losses are actually pretty big. So for example, by 2015, they look like they're roughly about 20%. So reducing or eliminating the wedges would increase aggregate productivity by 20%, which is equivalent to almost half a century's worth of productivity growth. You want to contrast these very large numbers with the estimates from the classic Harberger paper, where he estimated the losses in the US due to markups to be on the order of 0.1%, which is 2 orders of magnitude lower than what we can find. And these are due partially due to the fact that Harberger was working with a different sample, but also primarily actually due to the fact that Harberger was working with much simpler models that couldn't allow for the rich heterogeneity that's in the firm level data. So to see this, we can take our benchmark numbers for the 3 different estimates of the markups and vary the assumptions to see how the distance to the frontier changes as we simplify the model. So for example, if we throw out intermediate inputs, this halves or sometimes even reduces by a factor of 3 the distance to the frontier. Similarly, if we ignore the firm level heterogeneity and we just work with industry level data, we also lose much of the losses in efficiency due to these wedges. And so this again underscores that you really want to get these details as correct as possible. You want to think hard about the elasticities of substitution, the input-output structure, and disaggregate as much as you can to get reliable estimates. Now, these methods can also be extended to non-neoclassical environments. So for example, if you're interested in the entry and exit of new products into the marketplace, which is something that the old school neoclassical theory is not so concerned about, what we can show is distortions are still can be written as a sum of Harberger triangles. So you get the old sum of Harberger triangles that you would get in a neoclassical model with distortions. And now you get some non-neoclassical Harberger triangles that are basically triangles in the entry decision of firms. So this is the mass of different product types, and this is the wedge that's placed on the entry decision of these different product types. And once you allow for entry and you calibrate models with reasonable returns to product variety, this doubles the losses from misallocation due to markups once again. And so it highlights really that these details once again are important, and these forces are very, very powerful. So it's important for us to empirically try to understand them as well as possible. Now, everything I've been telling you so far has been about inefficiencies. So you might think that if you think the world is efficient, then you don't have to worry about these kinds of subtleties. But actually, as I alluded to at the beginning of the talk, Halton's theorem is not just limited by inefficiencies, it's also limited by non-linearities. So if you take an efficient economy and you think about subjecting it to shocks, of course, there's not just the first order effects if the model is not Cobb-Douglas, there's also going to be higher order non-linearities. And these higher order non-linearities are going to depend on non-linearities with respect to the productivity shocks themselves, and they're going to depend on nonlinearities that have to do with the cross partial between reallocation and productivity shocks. Of course, the terms that scale in the allocation matrix squared in efficient models are going to be equal to 0. So we don't have to worry about terms that look like this. And the reason is, if the model is efficient, then the first order term is always 0, and so the second order term will also be 0. But you do get these nonlinearities. But from Halton's theorem, we can also deduce that these nonlinearities are going to be captured by changes in the Domar weights, which are the first order terms. And now, thankfully, those propagation formulas that I showed you earlier can also be used to figure out what the changes in these sales shares have to be in a nonlinear model. So to a second order approximation, you can look at changes in Domar weights to get a sense of how nonlinear output is as a function of the shocks that you're hitting the economy with. And in fact, if you observe the Domar weights before and after the shock, then you can use a formula like this to get a handle on how nonlinearities are affecting output. And then if you can't see the shock, so if you're trying to make a forecast or a prediction, you can use the propagation formulas to deduce how the sales shares are going to change as a function of the input-output network and the elasticities of substitution. And once again, the details and the level of aggregation that you're working with is going to matter. So here's just a simple example to illustrate the point. If we go back to that horizontal economy that I showed earlier, and we just think about how output responds to a technology shock where no shock equals 0 to one of the producers, we can see that Halton's theorem or the Cobb-Douglas approximation is just going to give us a log linear relationship where the slope is given by the sales share of the producer that got the shock. But then the nonlinear response is going to depend strongly on the elasticity of substitution. If the elasticity of substitution is greater than 1, you get a convex function. And if it's less than 1, you get a concave function. And so, for example, this will have implications about whether or not Halton's theorem is going to overpredict or underpredict the effects of a shock. And it means that, for example, firm level shocks are going to behave very differently to sector level shocks. Whereas according to Halton's theorem, all we should care about are sales shares. So for example, by Halton's theorem, the fact that Walmart has the same sales share as electricity means that they should have the same effect on output, because they're both about 3% of GDP. The entire electricity generation industry is 3% of GDP, as is Walmart. But once you think about these nonlinearities, you see that probably the shape of the output function when you shock Walmart is very different to when you shock electricity. So here's a simple example just to illustrate that fact. So here I have a simple kind of electricity-driven example where you have a simple economy where the household consumes consumption goods, but some consumption goods need electricity. And they need it with some elasticity of substitution theta that's very close to 0. Now we know that the second order effect is going to just be given by the change in the sales share of electricity. If the sales share of electricity goes up when there's a negative shock to electricity, that means the output function is concave. Now we can use the formula that I showed you earlier to write the change in the sales share as a function of the elasticities of substitution and the input-output network. And if we apply it to this simple example, we see that we just get a linear combination of the elasticity in consumption and the elasticity in production. And as electricity moves towards being more and more of a universal input, so when M is equal to N and everybody has to use electricity, the elasticity of substitution in consumption drops out and only the elasticity of substitution in production matters. And so this means that because of the shape of the input-output network and the value of the elasticity of substitution, this function can be very concave in electricity shocks. So here's a more quantitative example using a quantitative model of the US showing how output responds in logs to a change in the TFP of two different industries. The two industries that I'm plotting are the oil industry and the retail trade industry. So on the x-axis, we have the change in TFP, where 1 means there's been no shock. And on the y-axis, we have the change in real GDP in the US. Now, what you can see here is that oil is plotted in red and retail is plotted in black. And the dashed lines are the first order Halton approximation, and the solid lines are the nonlinear response of the model. You can see that the dashed lines are almost on top of each other because oil and retail have roughly the same sales share in the year that we're calibrating. And so to a first order, they should have the same effect on output. However, output is significantly more concave in oil shocks than it is in retail shocks. And the intuition is because of the shape of the input-output network and the low elasticities of substitution with which oil is being used. The histogram in the background shows you the distribution of TFP shocks at annual frequency to different industries in the US. And so you can see that very often we're in the range of the parameter space where these nonlinearities matter for the effect of output. Here's another way you can approach the nonlinearities without using the structural model. So for example, here I'm showing you the global expenditures or the DOMAR weight on crude oil as a fraction of world GDP over time, from the 1970s to the late 2010s. And what you can see is that the DOMAR weight of oil started from about 2%, and the oil shocks in the 70s doubled it to about 5%, and then doubled it again to about 8% in the mid and late 1970s. So using the second order approximation, we can say that the initial effect of the shock to a first order should have been the DOMAR weight of oil times the reduction in the quantity of oil produced, which should reduce output by about 0.2%. But we can see that because the sales share of oil is increasing in response to these shocks, output must be concave in the shock. And so it's going to be worse than the first order approximation. And if we use the second order approximation using data on the shares after the shocks, we can actually see that the effect of the shock is multiplied by a factor of 3, which is another way to sort of see the same kind of nonlinearity. These nonlinearities, of course, are also going to matter over the long run, because when you accumulate shocks over long periods of time, they effectively get bigger and bigger because TFP shocks are permanent. And so phenomena like Boehmel's cost disease, where sectors with fast productivity growth shrink over time, can be seen as just another manifestation of these kinds of nonlinearities. So here I'm showing you the nonlinear growth in aggregate TFP in the US from the 1950s to today, as opposed to a first order approximation of how TFP should have grown during this period, and a second order approximation showing you how TFP should have grown. And what you can see is that Boehmel's cost disease has reduced aggregate TFP growth. These nonlinearities have reduced aggregate TFP growth compared to Halton's theorem by about 20 percentage points. But the second order approximation does a reasonable job of matching these nonlinearities. The last thing I want to talk very briefly about is everything I talked about today has been about closed economies. But these forces are also going to be very important when you think about open economies for similar reasons. And the method is also generalized to those environments. So here, for example, I'm showing you the gains from trade as you vary the assumptions for different countries, as you vary the assumptions about whether or not there's an input-output network, or whether or not you match the elasticities of substitution at the sector level. And what you can see is that as you vary the model and you make it more and more realistic and you take the disaggregated details more seriously, you increase the gains from trade by very dramatic amounts. So having input-output connections versus not having input-output connections doubles the numbers, and then putting in more realistic complementarities at the sectoral level doubles the numbers again. And so once again, while taking these shortcuts where you ignore the disaggregated structure are important and useful for qualitative things, quantitatively, it's really important to model them to try to get reasonable estimates. So I'm out of time, so I'm going to stop. To conclude, I think hopefully I've managed to convince you that it's important, given the fact that we have access to disaggregated data, we should try to take disaggregation as seriously as possible. And there's really a rich and beautiful theory in the background that allows us to think about how to disaggregate and aggregate back up using more and better disaggregated data. And I think there's already been an explosion of work on these topics, but I think much more is needed and much more can be done, both in terms of theoretical approaches and empirical and data-driven approaches. Thank you very much for your time.
Thank you very much for this really great presentation, David. So yeah, so I think informally we could take a few questions. So maybe I would start first. So my question would just be then about the the heterogeneous agent building block part of the equation. So what are some of the takeaways from that part of the picture? Yeah.
Sure, yeah. So the heterogeneous agent part, it has a variety of different implications. So one of the issues, so of course, once you allow for heterogeneity on the agent side, what you also have to take into account is that final demand is now an unstable object. So you can't treat final demand as if it's something that a single consumer is maximizing given income. And so changes in the factor income shares not only tell you about reallocation effects in the economy, but now they also tell you about redistribution of income from one consumer to another, because different consumers own the different factors. And this effectively makes it look as if final demand itself is being hit with preference shocks that are being driven by these factor income shares. But the propagation formulas are going to look similar. So if you have estimates of marginal propensities to consume and which households own which factors of production, then you can incorporate them into the propagation formulas and derive counterfactuals for what's going to happen. One thing that's very lucky is that heterogeneous agents for the sort of ex post results that I showed, like measuring aggregate productivity growth, having heterogeneous agents doesn't actually change those formulas. So the formulas that I showed today for example, measuring aggregate TFP continue to hold even in models with heterogeneous agents. But there's other objects that are very important in those environments, like real income for the different types of households, which now have their own formulas. There's really kind of interesting connections between the literature on the macro side from heterogeneous agents within complete markets and the trade side for heterogeneous agents that are trading with one another. And so you can sort of try to unify those and have one set of equations that speaks to both types of models.
Great. Great. Yeah. So let's see what we have. But if not, thank you for a great talk. Really enjoyed learning about your work with Emmanuel. It's really fantastic agenda. I remember seeing some slides, Bakay and Fari, 2018A, 2018B, CD. So it's very nice to have an overview today of all of it. Thank you very much for taking time to doing this.
Thank you. Thanks for giving me the opportunity. I'm glad that I was able to try to honor Emmanuel's memory in some way. Thanks very much.
All right. So we're gonna reconvene tomorrow after a long day of Zoom. Session A and then session B starting at 9 a.m. Eastern time again. And thank you for tuning in and see you soon.
Thank you very much to the organizer.
Thank you. Bye for now.
Thank you. Bye.